A qubit is the quantum version of a bit. Unlike a classical bit heads or tails, a qubit can be both at once. A superposition, Serra uno, on the block sphere. 0 is north. 1 is south. Measurement gives certainty on its axis, randomness on others. Two qubits span 4 states. 0, 0, 01, 10, 11. If inseparable, they're entangled. Example: O, 11 la raíz cuadrada de 2. A Bell state. Alice and Bob's results match on Z or X. Each outcome is random alone, but perfectly correlated together, something no classical physics can explain. In 1935, Einstein, Podolsky, and Rosen proposed a thought experiment to argue quantum mechanics was incomplete. Two particles separate, yet measuring one fixes the other's state. Spooky action. Einstein resisted, favoring locality and realism. In the 1960s, John Bell showed quantum theory could be tested via his inequality. Experiments later proved entanglement violates Bell's limits, revealing nature is non-local. Entanglement isn't just yes or no, it has degrees. One measure is concurrence. For a Tukabot state, arranging amplitudes in a matrix shows separability. If its determinant is 0, the state is separable. If non-zero, it's entangled. A Bell state has concurrence 1, separable states 0. But with mixed states, probabilistic blends of pure states, even mixing maximally entangled states, can erase entanglement, dropping concurrence to 0 and leaving only classical correlations. To bring this closer to life, our labs, here are some vivid examples. Quantum key distribution. Companies and labs are using pairs of entangled photons to create encryption keys, because any eavesdropper interacting with one photon breaks the entanglement and is detectable. This allows for unbreakable, in principle, secure communication. Quantum teleportation experiments. In lab settings, physicists have teleported the quantum state of a photon or other particle over distances, using entanglement plus classical information. The result, the state, is recreated remotely, although no faster than light transfer happens. Quantum computing error correction. Entanglement is used in error-correcting codes to protect quantum information. Entangled ancilla qubits help detect and correct errors without measuring the quantum data directly, which would collapse superpositions, decoherence, and fragile gardens. One experiment: superconducting qubits cooled to near absolute zero. The tiniest thermal or electromagnetic disturbance destroys the entanglement. Labs go to huge efforts, vacuum chambers, vibration, isolation, just to maintain entanglement for a short period. Story: there's a famous experiment where two diamonds, separated by 15 meters, were entangled via phonance quantized sound vibrations, and interference patterns observed showed the entanglement survived the separation. But even there, the entangled state decays. The uniformity of correlation weakens over time because of noise. Now, let's go deeper. What are the implications for how we think about reality? In an entangled pair, the whole has a definite quantum state. Each part does not until measurement. That flips our usual idea. We often assume knowing everything about a whole means knowing everything about parts, but not erre. Correlation without communication. Entangled particles correlate their measurement outcomes, but you cannot use this to send messages faster than light. That helps preserve relativity, even though the correlations are non-local. The collapse of the wave function seems non-local. Measuring one part of an entangled system instantaneously fixes the state for the other, even if light couldn't travel between them in time. Is this? Yes. But many physicists believe the non-locality is built into quantum theory. We just don't have any mechanism to send information in violation of relativity. Interpretations: many worlds, Bohmian mechanics, relational quantum mechanics, etc. talk about entanglement in different ways. Some say there is no collapse. Others relegate non-locality to the hidden variables. But experiments, Bell tests, have progressively closed loopholes, making alternative theories constrained. Decoherence, interaction with environment, causes the fragile quantum state to leak and lose coherence. Once coherence is lost, entanglement can be lost. Maintaining entanglement in physical systems qubits is hard. Scalability. as you add more qubits, creating entangled states across many qubits. Multiparty entanglement becomes exponentially harder. Noise, error, accumulation, physical control, isolation, all are challenging. Mixed states versus pure states. In reality, many experiments deal with mixed states. Mixed entangled states are sometimes mixtures of entangled pure states become separable overall. So one must measure carefully, for example, via concurrence or other entanglement. Monotone. Interpretational puzzles. What actually collapses? Is there a wave function? Is measurement special? Different interpretations give different answers. Though for engineering quantum technologies, often one can proceed without resolving philosophical debates. Here I'll bring in some newer recent insights from GLASP and recent physics literature that add depth. From Sean Carroll. What is quantum entanglement? Entanglement is not just a property of two particles, but deeply tied to quantum fields. Even empty space has entangled field modes. These entangled fields are foundational, and the correlations do not depend on spatial distance in the classical sense. From John Preskill, Esta discussions, quantum error correction uses entanglement not simply as a curiosity, but as a resource, encoded, distributed across many qubits, so that even if part is disturbed, the full information can be retrieved. So, what should you take away from all this? Entanglement is central. It's not a weird side note. It's likely at the core of quantum technologies, computing, communications, sensing. It forces you to rethink classical intuitions. Properties may not exist until measured. Locality can't explain everything. The whole can be more than the sum or the parts we can observe. Practical power has costs. Maintaining entanglement is hard. Scaling is hard. Environment is unkind. But progress is real. Labs are producing more stable qubits, photonic systems, entanglement over longer distances, even between space stations and ground. Use entanglement responsibly, scientifically. There are popular misuses of quantum terms, for example, quantum healing, etc. Knowing what entanglement is helps distinguish real physics from metaphorical or pseudoscientific claims. If there's one big lesson I want you to retain, it's this. Quantum entanglement tells us that reality is more deeply interconnected than our everyday senses allow. Two particles can share a single quantum state in such a way that knowing one instantly tells you something about the other, but not because of classical signals, nor because each had its own hidden secret all along. Entanglement reveals that nature at its foundation is holistic, not merely mechanical. So next time you hear about quantum in the news, or someone tries to claim that entanglement means telepathy or paranormal connection, remember, it's not about mysticism. It's mathematical, tested, weird, but grounded, and it may well be the backbone of the technologies of tomorrow. If you found this useful, hit subscribe. Drop a comment on what aspect of entanglement troubles you most. The non-locality, the collapse, or something else entirely. And stick around for the next video, where we'll look at multi-party entanglement, quantum networks, and what limits physics puts on all this.